Oh, sure. Yeah, you can go on.
Right.
Um,
Guys, uh, so this week, I just wanted to show some, I guess, opportunities that I found. And yeah, most of them are, I think, internships or no, education programs. So just like you go online or in person in the summer, you participate in like this training course for like both coding with algorithms and also working with the physical systems. I went to C2QA, so I can attest that I think it's pretty cool. It was online when I did it, but I think it's in person again. And the guy that runs it is really cool, and he will definitely give you any recommendations if you're just looking for people to do that. And otherwise, notable stuff on this list besides internships and stuff. There's the Q-Steam Quantum Influencer. So if you're just really good at like social media management and like just, I guess, being likable while also talking about quantum stuff, that's something to look at. There's Quantum Thursdays. So if y'all maybe want to look at some high-level quantum presentations over Zoom, or just look at recordings of that. There's also that. And there's this other thing coming up called Q-Rise, which is like this thing that Kate and I thought would be pretty cool for people in the group to collaborate on if you're interested. And did you want to go over it?
Yeah, there is a link there. So basically what it is, it's not a hackathon and it's not an internship, but it's something in between, which is kind of wait, why isn't Google Doc? Okay. I think it's an interest form, but I also have an email with that.
And it's coming up pretty soon, so it's on March 5th to
share this opportunity, which is basically you come together in a group of 5 and you go through some cool workshops, speakers, social events, and you all together do small, quick research projects over 6 weeks. And then you pitch it to industry sponsors, which include Kibara, Unitary Fund, Microsoft Quantum, Inflection, and Classic. Like, probably Microsoft Quantum speaks for itself, but all of these companies are basically cool world-beating quantum computers, quantum computing companies. So yeah, this is a really cool project for us to participate in. So we need a group of up to 5 people.
You can also just do it alone if you really wanted, but
I mean, yeah. I think if there will be more than 5 people interested, we'll just have 2 groups. But just to estimate the numbers, how many of you do you think would be interested in doing that? It's going from March 4th to April 12th.
So you said it's like mini research projects. What do you mean by that?
Okay. Q-Rise is a 6 weeks 6-week long research on hackathon.
And make the words bigger so we can also see it.
Can you what?
Make it larger. Human. Yes.
Yeah.
try control pause.
Sorry about that. Okay. Can you see it now, right?
Yeah.
Okay. So I'm not sure how beginning friendly it is, but I'm sure it will probably involve mostly coding and no like lab research that you need a lot of experience.
Yeah, and I might do it, so if anyone
Yeah,
is
we'll
a little
do
bit
it
shaky, we can
yeah.
do it together. We can learn together as a group. as a glove, pretty cool.
So yeah, definitely me and Donnie gonna take part in that. So and we're gonna have workshops, so that's a pretty cool opportunity for you to both learn and have already research experience in quantum computing that you can do in yours.
I sent you a link for the website that's a little more.
Oh, okay. Thank
Nope.
you. Okay.
You put that in the.
Yeah, I'll put it in the
I can just put it in the, I mean, if you wanna. Yeah.
okay. So the spreadsheet is in the group meet, just for you. And also, I don't see it here, but I'll just add you Waterloo. Summer school, that's where I'm going to this year, which is also like, it provides you with fully funded 2-week summer school in one of the biggest centers for quantum computers in the world, in terms of academic centers. And then they also sponsor your 10-week research project right after that, which is also a super cool opportunity. It's called I'm pretty sure it's easily. Okay. Any questions about that? How many of you would be interested in QRISE research project?
But how big, like big commitment is?
How big of the commitment?
No, yeah, more like how much background knowledge is required.
Like,
Because I looked
FAQ,
at,
it says like anyone.
yeah, because I looked at the website, they said like we don't need like a high level of.
yeah, I'm pretty sure most things like that usually don't require any experience at all. And even if you're stuck on something, and you feel like, oh, it's too much for you, like, I'm pretty sure other people in the team can lead and explain stuff to you. If that's something that is hard to, because it's gonna be not like individual project that you are lost yourself and don't know what to do, but it's gonna be like group discussion and collaboration. So even if you don't know anything, you'll see like an actual project being like solved and realized, and you see the process and you learn from that. So, okay, once again, just for me to count. Okay, not sure. Okay, I mean, you can join us and see like if it's gonna be too much, you can just drop it. Like, it's not a commitment.
Yeah.
Can you hold your hands? Yeah, I can. 1, 2, 3, 4, 5, 6, 7. Okay. I don't know what we should do. Hello, how? Are you interested in 6-week long low commitment research?
Yes, what ones?
Okay. We should, okay, I'll send the poll then in the group meet, just for you to have like time to think about it. It starts March 4th, so you have time to think whether it's something you want to do or not. So we can decide whether we do 2 groups or 1 group. I think of like 1 group could be better if some people wanna just like more like take part in it, but not like active part, more like observe and see like how it's going and learn from that type of thing.
Yeah.
And some people can be like more active. So
Well,
awesome.
and then there are also some more advanced opportunities for interactive students, that's for people who want something more movement. Yeah.
Yeah, and by the way, Waterloo also has a school on quantum computing for grad students. Now let's transition to actual lecture. So chapter 4, let's get into it. So, today we'll talk more about like formal math for like observations and measurements. And then we'll jump to actual interesting stuff, which is more like physicsy experiments of theory about EPR paradox and Bell theorem, which is basically like proves why time domain can be only described in quantum mechanics and not classical physics. But that's this one. So okay. In section 2, if you remember, we're talking about like measurement as a projection. Like if we have a photon polarized in this direction, and this is like 0, this is 1, or vice versa, it doesn't really matter. Then like the probability of this photon polarized in this direction being here would be like a squared and stuff like that. So we're talking about probabilities of measuring state in this, which is a probability will be a squared. But anyway, we're talking about measuring our state in projections on this sphere. And today we're going to talk about some math behind it. And and just to give some background reminders, for those of you who maybe missed some lectures last semester, I'm going to talk a little bit about bracket notation. Obviously, Tani covered it last lecture. Do you need to remind anyone? Anyone wants to go over bracket again? No? You good? Okay. So, complex conjugate of our state of our cat will be rock, and that's what we gonna use today a lot. So just to remind you about that. And if we multiply cat and rock, let's say of 0, that's basically just like flipped two flipped matrices, which gives us another matrix like this. So we basically take 1 time of this and 0 times of this, which gives us the matrix after that. And so basically what we see is that by multiplying certain states, we get information matrices that we saw last semester. For example, if we multiply 0 and 1, bra and cat and bra, we'll get a matrix that will result of flipping 1 state to 0 and 0 to null matrix. Null matrix means that it's going to be a state of 0, 0. Okay, and basically we can describe our linear transformations that we were talking about previously using this bracket notation, which is, I don't know if I like this desk anymore, honestly. So yeah, that's a new notation that we haven't really talked about last time. But this notation is called Dirac notation. And it's more like a formal math stuff, but you can need it pretty often in quantum computing. So let's say we're talking about bit flip gate, which we saw 1,000 times so far, which is X gate. Basically, in bracket notation, we can express it like this. Okay. And what we'll get in the end is some sort of like matrix. It's gonna look different, obviously, but the matrix that will flip 1 to 0 and 0 to 1. And that's basically a Dirac notation. Yeah, that's what we're gonna get. This will be 0, 1, 1, 0. So if we multiply it on 0, 1, we'll get 1, 0, and vice versa. If we multiply it on 1, 0, will get 0, 1, which corresponds to 0, and this corresponds. So that's more like a reminder stuff. And to generalize Dirac notation, it's written down on your handout, if I'm right. It should be this. I don't know if I want to write it all, but it's written down in your handout. And are there any questions about that?
Are you saying that the 0 cat is both the 0, 1 and the 1, 0?
This is multiplication.
Oh, my bad.
Yeah, this is x gate multiplied by, this is 1 state, and it flips this to 0.
Oh.
So I'm just saying that linear transformations that we're talking about as matrices can be represented in Dirac notation. Dirac notation is just like we basically say that this matrix can be expressed in terms of our basis states in bracket notation. Okay, can I erase it? Yeah, no more. Yeah, and the other marker that is not permanent, like you can barely see it, and like I cannot record it there. So. Okay.
I have one.
Oh, you have one? Oh my god. Thank you so much. Oh my god, this is so much better.
Wait.
This is late. So the other thing that we're gonna cover today before we actually push into cold physics, but that's something that you need to know if you wanna go to quantum computing or will ever work with it. And we'll talk about some Hermitian matrices, and basically that's the matrix O for which its complex conjugate is equal to itself. So the other thing that we know about them is that its eigenvalues are real. And just for those of you who don't know, if we multiply some sort of matrix on some vector, and it's equal to some just like value times times this vector, then this is eigenvector and this is eigenvalue. Eigenvalue is just like real or complex number, but if you talk about Hermitian matrix and this is real, means there is no eigenvalue, no imaginary component. It's just like 1, 2, 3, and so on. And so, okay.
You know that all of the observables in quantum mechanics are, I guess, extracted from these quantum states mathematically. You agree with that?
Yeah.
Okay.
We're gonna talk about what observables are, but yeah. And so in quantum mechanics, we use this eigenvalues of O to like describe energy and stuff like that. But in quantum computing, we don't care about values of eigenvalues. And so what we care about is that they're distinct values and they're different, but we don't care who they are. We can use 100, we can use pi, we can use 1. as long as they differ, they represent different states for us, and that's what matters here. And the other thing, so they are basically used as labels. The other thing, that we're gonna talk about is what Donnie mentioned, is observed. So we basically use Hermitians to describe observables, and I want to specify that it is not how to say it. We don't use it to like observe the state, rather we use it to like specify certain states and subspaces of our observation. I'm gonna get into more like numerical examples so you can see what it is. So basically, let's say we have some subspace V, some vector space V with subspaces S and S perpendicular, which means basically that we have like certain states that are perpendicular to one another. This is like S, this is S perpendicular, which can be like 0 and 1. So that's one of the requirements when we're talking about them. And so let's say that S can be generated by 0, S perpendicular can be generated by 1. So, okay. The other thing that chapter goes into a lot is like some boring math, a bunch of like specified theorems that are super hard to read, especially later in the evening. And it gets super boring, but basically what it talks about is that there's some projectors, and projectors are basically the Kedra notations for certain states. And so, as I said, we're free to use any eigenvalues that we want to specify a state and observables. One of the most popular observables that we're gonna use is, let's say, O is equal to some eigenvalue 1, then 0, then eigenvalue 2, then 1. That's a general form of a certain observable. Let me move here. And so, for example, an observable for basis states will be Z, which is basically what we wrote, but with minus signs in front of ones. And so let's look at what it will give to us. So we can write it down in terms of matrices. For example, this will be 1, 0 times 1, 0 minus 0, 1 times 0, 1. And so if we calculate it, it's basically going to be 1, 0, 0 minus 1. And so what it does basically when we multiply it by a certain state by is that if we observe 0, it says 1. If we observe 1, it says minus 1. So now it makes more sense on why we use just different eigenvalues, but we don't care about what eigenvalues we use. It's more like a label. And here, like minus 1 is labeled for 1 state. 1 is labeled for 0 state. So it's just a convenience. We can use like 3 and 4 and stuff like that. But basically, what it tells us is what we had as an outcome. And I want to get into a specific example. So in the book, there was one of the examples that I wanted to specify. By the way, how are we doing on time? I don't really. Is it 7:59? Oh, okay. So it says design an observable for 3-qubit state. That basically distinguishes between same value states and everything else. And so it can sound a little bit confusing, but basically what we have is that we have certain states like 0, 0, we have certain states like 0, 0, 1, and so into force when we observe. So we have like a combinatorial problem here. But we are interested in distinguishing all same value states in the end. So basically, we can design this observable in a way that, let's say we use value 3 for the states 0, 0, 0 and 1, 1, 1. So we write down 0, 0, 0, then we use our projection 0, 0. So that's the requirement to write it, and then we do plus 1, 1, 1. 1, 1, 1. And then we specify, let's say, another eigenvalue. Donnie, what number do you want to use?
5.
5. Okay, and then we write 5, and in brackets, we write all the other numbers like 0, 1, 0, 0, 1, 0, 0, and blah, 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 all the other options that we have. The convenient trick that we can do is we can just like put 0 here, and so it will just vanish. And so we'll say that eigenvalue 2 will be 0. But it doesn't matter. What we know is that if observable says 3, then we know that we measured all qubits in the same way. If it measures 5 or it measures 0, then it means that something is different in this thing. And this is a good example of how observable works. So it just like allows us to receive an answer to like our question of how our outcome looks like. Okay, are there any questions about that? Okay. So for example, our observable or basis states, I just wanna specify that it doesn't measure a state, rather it gives us an example of outcomes. So this is our Z that we specified before. And so if we have a state 5 that is A0 plus B1, it multiplied on 5, what we'll have is A minus B. And this is not equal to A minus, oh no, what am I writing? This is not equal to A minus B1. So this is not it. This just says that this is the amplitude that we're gonna have if we measure A or if we measure B. So just to make sure we're on the same page with that.
I think. Well, also just to add on that, the representation of multi-qubit states usually is translated to binary. So the eigenvalues that you would extract from those multi-qubit states would be like, say, if it was 1, 0, 0, it would be 4. If it was 0, 0, 1, it would be 1, 0, 0, 0, 0. Yeah, that's a little note there. So.
Yeah, and there, okay. Are there any questions about math part? So I can actual physics. Okay. So the second part that you can see on your handout talks about EPR paradox and Bell theorem. So what it basically is. So later in last century, Einstein and some other people like Podolsky and Rodin wrote a paper where they questioned if we can like describe our world completely with quantum mechanics and stuff like that. And there were a bunch of like series of experiments that came up after that. And today we'll specifically talk about EPR experiments. What is EPR? It's basically an abbreviation for Einstein, Podolsky, and Boltzmann, for like the people who wrote this paper. But I think they're not the one who like did all those experiments still. Anyway, we're generating a Bell state, which is an entangled state, which is 0, 0 plus 1, 1. So it's basically two photons that are polarized in one of these directions. And we send one photon to Bob. And we send one photon to Alice. So just to remind you how photons are polarized, we have like polarizing filters. And when we send a photon, it can have a certain vector, just like our qubits do. That's like the most simple form of qubit. And so this is like photon vectors. And this is like our axis of polarization. And basically it either goes through this axis and getting polarized through this axis, or it's getting absorbed through the filter. And that's like the stuff that we talked about during the first week. So they basically do the same here with qubits. They represent them in this entangled state as photons that they then polarize. And so they send one photon to Bob and one photon to Alice. And so Alice and Bob both observe them, and Alice observes the first photon from this state. So this is identity matrix. What it means is basically we apply observable to first qubit and apply identity matrix, which doesn't change the state of second qubit. And Bob's does the opposite. Which can be like another observable. It doesn't really matter here. And basically experimentally what we see is that if Alice observes 0, then Bob definitely observes 0 too. If Alice observes 1, Bob's observes 1 too, and vice versa. If Bob observes one state, Alice observes the same state. And we talked already about it as a entangled state, but the paradox here is that you might think that information travels from Alice to Bob with a speed greater than speed of light. But basically, it doesn't really work like that from the point of special relativity, because then it would mean that like somebody measured it first, and then information travels to another person and tells them, oh, she measured it in this state, so this is your state now too. But in special relativity, it could be possible that some other observer here, let's see, Donnie observes both Alice and Bob, and depending on his position in velocity, he could observe Alice, observing first, and then observing Bob, whether like in the frame of Bob, he would observe it first. So like different observers can observe it in different sequence. So that's why basically information cannot travel here with greater than the speed of light. That's like a simplified explanation of that. And so it starts raising a lot of questions. And one of the theories that people came up with was basically the proposition of local hidden variables. And this is the classical theory that people tried to explain this phenomenon on entangled states with, which is basically they were like, okay, in a particle, there must be like a variable that we cannot measure, but it like fluctuates with time. And because we like shove these two particles at the same time, they have like same local hidden variable that like fluctuates at the same time. And that's why they observe it at the same time with like same value. That was the theory, and people basically not like believed in it, but they were trying to like search for this local hidden variable, which would make the situation classical and describe it completely. And so basically this theory was also kind of popular to describe this phenomenon until 1964, when Bell came into play. And you heard of this dude? He was basically the state is named after him. It's Bell State. But what he did is he proposed another theoretical experiment, and then it was like also, it was also performed actually. Oh, I can probably flip it. So now, now we do basically the same thing. And you have the picture on your handout. There are some like weird arrows going on here, and let's see what's going on here. So basically, now we give Alice and Bob same polarizing filters, but one is located vertically, while others are located with 60 and minus 60 degrees of polarization. And so they basically randomly pick the polarizing filter each time. And so according to quantum theory, because they're basically picking filter with basically randomly, the probability, let's say, of picking it vertically would be 1/3, and then picking it with either 60 or minus 60 degrees will be 2/3. So that's the first thing. And then basically we can come up with observables that from this from what we just covered with observables, say that the observable will be cosine theta for polarization single theta 0 plus sine theta 1. And there is a lot of math going on behind it that proves it in the book. I'm not gonna go over it right now. But basically what it does is it says that for measuring qubit with theta, we have the probability. Proportional to cosine of delta theta that we have. So for basically going up, our delta theta is 0, and then for either 60 or minus 60, our theta is 60 degrees. So we have a probability of finding state here to be cosine of 0, which is 1. This will be 100%. And this will be 2 times third, and then cosine of 60 will be 1%. This will be. And also, so here we'll have that half of this also agree and half of this also disagree, which in the end gives us 50% of photons agreeing and 50% of photons disagreeing in value, like 0 and 1. And so in short, if we take the same thing with, it's like a lot of mass, a lot of combinatorics. But basically, if we make an assumption about local hidden variables for all our polarized axes, so like local hidden value 1 until local hidden value 7, well to 7, because we have 2 to the power 3 options, which gives us 8. It's basically combinatorics. And let's say one time it's observed, one times it's I forgot the word, polarized. Yes. So let's say observed, 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 and observed, polarized, polarized, and blah 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 blah. We'll have 8 options of that. So basically, what we say is that that is the option for one photon. And then if local hidden variable is a true thing, then the other photon would have the same qualities as that. How confusing is that so far? Because I was really confused when I was reading it. So basically what it says is that if we count all the options here, in the end, we'll have, what do I have here?
Any questions so far?
Yeah, I feel like I lost everybody. Okay, you can read the book for that, because it's a really confusing movement. But basically, in this theory, only 5 nines will agree, and 4 nines will disagree. And experimentally, it was confirmed that the ratio should be around 50-50. And this classical assumption completely was proven wrong. So that's how local hidden variable assumption was proven wrong. Is that clear at least? This thing was local hidden variable. Okay. So there was a whole research of Bell and his revolutionary thoughts just here in 2 minutes. Yeah, are there any questions in general?
I did my research on Bell's theorem, and
Oh, okay.
you almost have to like read the textbook about 20 times before it starts to make any sense.
Yeah, I was also like, it took me a while. I was like, what? But yeah, it's an interesting theory, and it's an interesting way to like prove it. You can definitely read chapter 4 on that. I think it does a great job summarizing it. But yeah.
Nobel Prize doing this, right? This was the Nobel Prize 2 years ago.
2022,
So,
John Clauser.
so it's not gonna be like too simple. There was someone.
Yeah. Yeah, but it's like really cool theory. I like, if you don't get it, but you're like interested in that, I definitely suggest reading it. And yeah, I'm probably not the best in like explaining it, but it also is like hard to get. So don't be stressed if you don't get it super fast. That was the last thing that I wanted to cover today. So thank you all for coming today. And I'll send the call about the research thing. Definitely should participate in that. By the way, what about next week's meeting? How do you feel about midterms? Should we cancel the meeting, or do you still want to come?
Who's got midterms next week? You want?
Tuesday.
So you good for Thursday? Okay, awesome. Thank you so much all for coming. If you have any questions, feel free to speak after.